All right, this time we have a vector position that's given as a function of t. So, all right, it says a 0.1 kilogram particle will move according to r of t equals 4 minus t squared I plus 9/4 t minus 3/16 t cubed j, where r is in meters and t is in seconds. Can you plot the particle's position for the times of 0 to 4? So first thing that I do with these is make a table. And what you want is you want a table of t, and then you want basically your x component and then your y component. So you can pick the times here that you think you need to see in order to tell what the path is. So it would make sense, I think, to do, let's say 0. We might want more information. We might want like 0.5, 1, 1.5, 2, 2.5, and so on. I'll just start by calculating the integers, and then we'll see if we need more in order to tell what the path is. So first for x, just plug in a 0 into the x component of that. So the formula, of course, is 4 minus t squared. That's what gives you your x. And then for your y, you'll have 9/4 t minus 3/16 t cubed. Alright, so for my x here, we would get 4 to start. Then if we plug in a 1, we get 3. If we plug in a 2, we would have 0. And if we plug in a 3, we'd have 4 minus 9, which is -5. And then a 4 will make -12, it looks like. Now plug those same times into the y component, which is this component. You'll get 9/4 times 0. Yes, that's just going to be 0. Then you get 9/4 minus 3/16, which is 33/16. Approximately 2. I'll just put the approximate. Well, 2.0625, okay, decimal. Then, let's see, 9/4 times 2 minus 3/16, so times 2 cubed. It's apparently 3. Alright, great. So let me plot those and see if we can have some sense of what the particle is doing. So we want to plot 4, 0. That would be this point right here, and that is the starting position for our particle. Now it's going to go to this point here, 0, 3, which is an intercept, which would be here. That is t equals 2. And then we have -12, -3, which would take us to here. T equals 4. It's tough to tell, what it's doing so far. So that's why I wanted to include just a little bit more data here. Let's plot these points and see if that gives us more insight. So 3, 2, it's like this. And then -5 and 1.68, that'd be like here. Yeah, I think it's pretty clear now what's happening, right? So it's taking a path. It just looks like this kind of thing. Something like that. Then we could show the direction of the path with arrows. So notice that it is going from t equals 0 to t equals 4. So this is the start of the path, and this is the end. All right, that's great. Now we'd like to find the velocity of the particle at a particular time. So for that, we're going to want to differentiate. Okay, because this is a position in r. So we want v as a function of t will be the derivative of the position function with respect to time. So you have to differentiate each of the formulas separately. Alright, so we'll get negative 2t, it looks like, for the I component. And then here we'll have 9/4 minus 9/16 t squared j. I would bring the 3 down, multiply by that 3, and then reduce the exponent by 1 when I do the derivative. Alright, but they want it at a particular time of 2, so we can now plug 2 in. So we'll do v 2 seconds will be negative 2 times 2 I plus 9/4 minus 9/16 t 2 squared j. Alright, so v of 2 is negative 4i plus 0 j. Alright, now we want to be able to plot that. So what does it look like, and where is it located? It's going to be located at t equals 2, because that's what we plugged in. But it's a velocity vector. And so we just want to draw a vector who has a component in the x direction of negative 4 and no vertical component. So which way does it point at that spot? Left, right, up, or down? It points left. And so what we're seeing there is that the velocity is it's tangent to the path of motion. And so that'll be v of 2. Next, it asks for the acceleration of the particle at t equals 2, right? So we'll want a of t, which will be the derivative of the velocity with respect to time. So we want negative 2 I minus, I think it'll come out to 9/8 t j. Because I would bring the 2 down, multiply by the 9, that makes 18/16 divided by 2 on top and bottom, so 9/8 t. Yeah. We have to plug in a of 2, which would be negative 2i minus 9/4 j. So now we want to just go to this. This one looks good. And then this one should be 2.25, which is about that long. Alright, so our total acceleration then is going to be something like that. That's the total. Then over here we have a tangential component of acceleration, and over here we have a c, the centripetal component. So if we want to give a number for it, AC is negative 9/4 J, and a tan is negative 2I. Okay. Find the vector net force acting on the particle at t equals 2. Alright, so for that, we just want F net as a function of time will be the mass times the acceleration as a function of time. Now our acceleration formula is right here. So we're just going to multiply the mass. The mass of the particle was 0.1 kilogram, they said. So, okay, let me do it over here on the side. Okay, when you do the vector net force, you want F net as a function of time equals mass times the acceleration as a function of time. Now, the net force then is given by the mass that they gave in the problem was 0.1 kilograms. So that's the scalar to multiply everything by. And then what you do is you just put your vector acceleration in here. And so that was negative 2I minus 9/8 TJ. So that was the acceleration that we found in the previous step. And you just have to distribute your 0.1 to the terms. So your F net becomes negative 0.2I minus 0.1125 TJ. Alright, that looks good. Now find the magnitude of the force acting on the particle at t equals 2. So first I'll plug in 2. So we'll get negative 0.2I minus, looks like 0.225 J. Alright, what's going to happen is the force is going to go along with the acceleration. They're going to have the same vector direction because it's just a scalar mass times the acceleration. So like our force will just point in the same direction as A. So that could be F. Like it's a little, I increased the scale of it. It should be much smaller, but that's too small to draw. Okay. So that's the vector version of it. If we want the magnitude of it, yeah, I should have arrows on these heads here because these are vectors. But when we want the magnitude of it, just take the square root of the squares of the components. I get 0.301, and the units will be newtons. Finally, find the direction of the net force acting on that particle. So it's 48.4 degree angles, so theta standard is 180 plus 48.4, 228.4 degrees, or 228 degrees.